This is PS33BBlake for Thursday, second video, pages 84 and 85. We just did Newton's first law, which says objects tend to keep the motion they have. And by the way, the more mass they have, the more they have that tendency to keep that motion. You know, you got a cow running full speed, you don't step in front of it, versus if you have a, I don't know, kitten running full speed, that's not going to knock you over. Newton's second law is that equation, F equals ma. Net force is caused by mass times acceleration. Newton's third law says when one object pushes on another, the other object pushes back. And they have to do this for the same amount of force and the same amount of time and the same amount of momentum. There's no way to undo that. It states that when one object exerts a force on the second object exerts a force back on the first that is equal and opposite. You may have heard of the expression, for every action, there is an equal and opposite reaction. This isn't the first time you've heard this in school. You've studied Newton's laws before, probably. So forces don't cancel, really, they add. Now, opposite forces may add to zero, but they don't really cancel as much as they add. See figure 13, page 84, which is this person pushing a refrigerator box or something down here. If one force, and I can't draw the box and the person, so I've simplified it here. But if there's a 30 Newton push this way, but the floor is exerting 30 Newtons of friction, it's not going to accelerate. It's going to keep the velocity that it has. And its velocity probably starts at zero, and it's going to keep it at zero. But the point is the net force is zero, because 30 positive minus 30 is zero. Now there's forces there, but when you add them, they sort of cancel out. Now on the other hand, if the friction's only 10 and you exert 30, and you subtract 10 of friction, it's going to accelerate because there's a leftover 20 newtons that's going to accelerate it that way. And that's called a net force. Okay, so 15. Describe. You need to read that section. All of this was delineated in the Google Classroom. Let me show you here quick. Okay, read 80 to 85. You may already have done that. Complete 11 to 14. You probably already did that. And then these section review questions. So this is the last of it for Thursday. It's a short day for you, actually. Uh-oh. I don't know what happened here, but it doesn't like what I did. Oh, I'm over here. This is the problem. Okay. 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 So, use Newton's laws to describe all three of them. What's going to happen when you kick a ball? Okay, Newton's first law says the ball has mass, the ball has inertia, it doesn't want to go anywhere. And you are adding extra force on one side that's not balanced. That means the ball is going to accelerate. Newton's second law says F equals ma. The ball's acceleration is equal to the net force, which is your kick, divided by the ball's mass. And that's the one we're going to pay attention to, and probably for this purpose could ignore like gravity and the ground pushing up. But all the forces up, you're going to pay attention to the kick. Divide that by the mass will tell you that ball's acceleration, which is going to be quite high. And the third law states that as you kick the ball will actually also exert a force on your toe, equal and opposite. So you may have to kick it a certain way or wear a special shoe or something like that. I know in football, the kicker usually wears a special weird-looking shoe. Number 16. Explain why Newton's first law of motion is sometimes called the law of inertia. So the more mass something has, the more of a tendency it has to keep the motion it's already got, even if it's zero, and not accelerate very much. So inertia is the property of an object to resist a change in motion. Newton's first law says that an object's motion does not change unless there's an unbalanced force. And the bigger that unbalanced force, by the way, the more it may change the motion. All objects with mass have inertia, and the more they have, the more inertia they have. Imagine if you're going down the highway on a motorcycle and a mosquito hits your hand. You're probably not going to notice. Now, maybe you've done this though. You're going down the highway on a motorcycle and you've hit a dragonfly or a bumblebee. Smack, leave a welt. This is more inertia. You wouldn't want to hit a bird or an owl or something. Cars hit birds too, and we keep driving cars, so connect those dots. We're not going to quit driving cars just because they hit a bird. I'm not going to. Number 17. Describe whether the inertia of an object changes as the object's velocity changes. So an object, let's say, goes faster. Does its inertia get more? That's a good question. Does it have more tendency to change its motion or less? Nope. Its inertia is almost the same thing as mass. It doesn't really have anything to do with velocity. Let's stay away from the discussion of what happens when you're going extremely fast, like near the speed of light. Okay, that's weird stuff. But, you know, if you're like the speeds of bullets and slower, it's going to have the same tendency to speed up or slow down, regardless of how fast it's going. Now, other things may happen that are complicated that we could discuss in physics class that we're not even going to get into here. But its inertia won't change just because it's moving fast. 18. Explain why an object with a smaller mass has a larger acceleration than an object with a larger mass if the same force acts on it. So by Newton's second law, an object's acceleration is force divided by mass. So the larger the mass, the smaller the acceleration. You've studied this in math class. If this force stayed the same, it says same, and let's say, what happened? 18. If the acceleration went up, it had to be because the mass was smaller, because if that went to double, this has to go to half, and 2 times a half is the same number. So they're inversely proportional. So an object's acceleration is net force divided by its mass. So the larger the mass, the smaller the acceleration. And if you take an engine and you put it in a car, it's going to have a certain acceleration. If you put that, well, its acceleration is going to change, but that's a whole different thing. But if you put that same engine in a dump truck full of gravel with way more mass, the acceleration is going to be way less. It's going to take way longer to get up to speed. Number 19. You push a book across the table, the book moves at a constant speed, but you do not move. In reference to the surface of the earth, identify all the forces on you, then identify all the forces on the book. Okay, this is actually a hard one. Let me explain this diagram. In the diagram, I can't draw a person, so this represents a person, a vertical rectangle. And here's the table leg, and here's the table top. So you push on the book, but the book pushes on your hand with an equal force. Now let's see what this says about the motion of the book. Book moves at a constant speed. Good, because that makes this easier. And the book is moving, and the table is exerting a friction force on it. But it's got this equal and opposite force that's ultimately supplied by you acting on it. So it's going on at the constant speed. It's not speeding up, it's not slowing down. Plus, gravity's acting on the book, and the table pushes the book back with an equal and opposite force. So there's nothing happening this way. It's not accelerating this way. All these forces balance, cancel out with an opposite one. So they aren't making this speed up or slow down either. It's constant. You have a force against the floor, and the floor is holding you up, and those cancel, so you're not accelerating up or down, you're staying put. and you have friction against the floor, and you're pushing on the floor, and the floor is pushing on you, but you're stuck together, and those forces are equal, so you're not sliding back or sliding forward or to the side as you push the book. So as the book moves across the table in a constant velocity, all the forces are balanced by another force. And so nothing accelerates. The book's moving, but it's not getting faster or slowing down. 20, calculate acceleration. Okay. Calculate acceleration. Okay, so in this case, a student pushes on a 5 kilogram box with a force of 20 newtons forward, and the friction is 10 newtons backwards. So if the book is forwards this way and the friction is backwards this way, and this is bigger, 20 minus 10, there's still 10 newtons of leftover force. Now, leftover force, when we add them up, that's not zero. We call that net. That's all that means. If you add the forces up, if they're not balanced, there's a leftover. That leftover net force, 10 newtons force, is what's going to cause the acceleration. Here's Newton's second law. Net force is mass times acceleration. So I'm going to put a 10 here. And it's a 5 kilogram box, so I'm going to put a 5 here. So to get the acceleration, we're just going to divide 10 by 5. We're going to divide both sides by 5. And we end up with 2. And the unit that's left over is newtons per kilogram. It's going to end up being meters per second squared, because a newton is a kilogram times a meter per second squared over a kilogram. Kilogram cancels, meter per second squared is left. So you can write them as newtons per kilogram. That's fine. Book tends to do that. You can write it as meters per second squared. That's fine. Last question, 21. You push yourself on a skateboard with a force of 30 newtons east and accelerate 0.5 meters per second squared east. Find the mass of the skateboard if your mass is 58. Okay, so on this one, what you have to do is put the numbers in. And you find 30 newtons is the force, and 0.5 meters per second squared is the acceleration. When you solve this for math, you're going to divide 30 by 1/2. What do you get when you divide 30 by 1/2? Meters per second squared cancels over here, but to be equal, you divide it by 0.5 meters per second squared here. A newton is kilograms times a meter per second squared, because the meters per second squared is canceled and you are left with kilograms. And 30 divided by 1/2 is 60 kilograms. So if you and the skateboard are 60 and you're 58, what's the skateboard? That's the question. Well, if the total is 60 and yours 58, the skateboard has to be 2 kilograms. Or I've had a student do a fancy pants algebra solution with it that looked like this, so I was kind of impressed they used their algebra from algebra class for that. 58 plus m. Okay, so you have that ready to go. Turn in your paper. You got it off here. You can pause it, write stuff down, go back. CART's investigation 2 is up as soon as we finish with number 1, because we've got this out of the way. CART's investigation 2 is about friction.